Okay, welcome back to day 2. Again, getting back into our note taking, make sure that you are turning to a blank sheet of paper. We're putting notes that we took yesterday kind of to its side. We're going to continue with today with the new set. So again, make sure that up at the top right-hand corner, you're writing down the topic, which is going to be our coolant system. You're writing your name, and then today's date, which is the 23rd of October, 10/23. Okay? Yesterday we ended off, we talked about radiators and how they can either be a cross flow or a down flow. Okay, the two different kinds of flows. The reason why we don't use down flow is just due to the fact that it's a much taller radiator, and the grills on most of our modern day vehicles are much smaller due to the fact that we want to be more aerodynamic, okay, because then we can get better gas mileage. So manufacturers right now are preferring the cross flow. It's a much more efficient system to be able to put fluid in or coolant in at the top, and then it goes across and down instead of just going straight down. Okay. Now, with that being said, radiators can be made out of different materials. More common than not, the fins on the radiator are going to be a metal, typically aluminum. Okay, because aluminum is lightweight, it can conduct heat fairly well. Okay, so that way the coolant can take that heat and discharge it into the air through convection, and then cool it down, get it back into the engine. However, we are starting to see not just a completely aluminum radiators. We are seeing parts of the plastic added on to the aluminum fins. Plastic is also lightweight. It's very durable. It's resistance to the potential corrosive properties of the coolant. But the radiator core themselves will still be metal. Right, Chase?
I wrote it down. What?
Emerson, you can sit right there.
But what about Roto?
Yep, that's going to be his new spot.
How's that fair?
You're correct, it's not fair.
He just rubbed it in my face. No did he? Just one day. Just give me one.
No,
chance.
Chase can't handle
Yes,
it.
I can.
No, you can't.
He wasn't even talking.
I have my stuff written down, and then I have.
Yeah.
And I'm looking for my notebook.
Yeah.
Emerson, please sit in your assigned seat. I'd appreciate it. Thank you.
Class and I'm looking for my notebook.
All right, air conditioning condenser. We talked about how sometimes the automatic transmission fluid cooler can be integrated into the radiator, or it could be a completely different system. Typically, when you go and look under the hood, it's very easy to find the radiator because it's a large component. But often, depending on where you're looking at, you might actually come across the air conditioning condenser, which is going to typically be in front of the radiator. It's much smaller. Okay, and again, coolant is not going through that particular component because it's part of our air conditioning system. So refrigerant is going through that. But how the radiator takes the heat away from the coolant through convection, the same process is occurring in our air conditioning condenser with our refrigerant. Okay? We'll get more into air conditioning like in May when it starts to get hot out again for summertime at the end of the school year. But just note, the heater core in our coolant system is there to heat up the inside of our cab, right? Our air conditioning system with the condenser is designed to do the opposite of that, to cool the inside of our cab. All right, it's a very kind of interesting scientific way of how we do things with that. So, just so you are aware, if you see a mini radiator in front of the actual radiator, that's the AC condenser. Don't get them confused. All right, next component that we're going to talk about, we got our radiator cap. The radiator cap is a very critical very critical component in the coolant system. It's very technical, even though it might not look like it because it's just a cap, right? You buy a gallon of milk, it's got the little cap you twist on to hold it from spilling, okay? The radiator cap is more than just holding in the coolant, all right, although it does do that. So typically on the radiator, you're going to have a filler neck more often than not. So if you are ever low on coolant, you can add more coolant directly into the radiator, or more likely the reservoir tank, which we'll talk about here in a little bit. But some older vehicles, you add it right to the radiator. Then you put the cap back on. That cap seals the coolant system. Okay? This way we can actually pressurize the coolant system. We'll talk about why we do that here in a little bit. It also is going to help relieve excess pressure that's being built up in the coolant system. You know how we talked yesterday about the hoses? And the hoses have an internal spring?
Yeah.
Okay? And that the reason why we have those springs in that hose is so that way as the coolant system expands, it can stay rigid, or as the coolant system might be cooling off, we don't want the hoses to collapse on itself. Okay? So as we pressurize the system, that could expand things. So just kind of keep that in mind. The radiator cap, in this case, if we do start expanding, has the capability of dealing with that expansion by siphoning out some of the coolant from our system and then returning it as it cools down and it contracts. All right, so there's quite a bit of functions here to the radiator cap. It's not just simply something we screw on and then we're done with it. If you have a malfunctioning coolant system, it could very well be linked to this cap malfunctioning. And it's a very simple fix because it's usually right there in the front. Pop that old one off, put a new one on. That might solve a problem, okay, depending on what the symptoms are. And when you go out in the lab next week, for part of the lab, you're going to be pressurizing the coolant system to see if it holds. And then you're also going to be pressure testing this radiator cap to see if it is functioning properly. We'll get more into how you do that, but it's a very simple test, and it's one that you can use in your toolbox to help diagnose if there's something wrong with the system or the cap. Now, we talked about how a radiator cap is going to help pressurize our coolant system. Why do we want to do that? Well, for every 1 pound of pressure that a radiator cap holds in a system, the coolant boiling point is raised by 3.25 degrees Fahrenheit. I don't get it, Mr. Getsky. Why do we want to raise the boiling point? Well,
Then it won't boil.
right? That's kind of the idea. What is the main component of our coolant? Or I should say, typically 50% of our coolant. What do you think it's made out of?
Water.
Water. Okay? 50% of our coolant is water. What temperature does water boil at?
212 degrees.
212 degrees. Okay? Now, what's the operating temperature of my engine?
180 to 210.
Okay, 180 to 210. Boiling is 212. What do you think the odds are that we're probably going to hit 212 degrees at some point?
Pretty high.
Pretty high.
Like almost guaranteed. Maybe. Okay. So what we're going to do is we're actually going to pressurize the coolant by a couple pounds of pressure. Now all of a sudden we add 3.25 degrees Fahrenheit to our boiling temperature. So no longer does water boil at 212 degrees. Instead it's boiling at like 216, 220 degrees Fahrenheit. Okay? We're raising that threshold up because we don't want to boil the water. What we want to do is we want to have the coolant pick up the heat and carry it away. if we boil the water in our coolant system, guess what we've just produced?
Boiling water.
Boiling water, which is what? It's liquid water turning into
Evaporation.
steam, right? It's going to turn into
Steam.
pockets of air inside my coolant system. If I have pockets of air in my coolant system, the coolant is not directly touching the components that are hot, which means it can't pick up that heat and transport it away. Which means not only am I boiling the liquid in there, but now I can't cool the engine as effectively as I once was because all the liquid was touching. Does that process make sense in terms of why we don't want that water to boil? Right? It's kind of a twofold whammy. So we pressurize the system, increase the temperature of the liquid in there so that way it doesn't boil. The fun part is some of you might know that if you're driving your vehicle, right, and your engine's overheating, what's the one thing you absolutely do not ever want to do with your coolant system? Pull over to the side of the road, you open the hood.
Don't open the cap.
Don't take the cap off on a hot engine, okay? Why is that?
It's pressurized.
It's pressurized, okay, which means the boiling point is higher up, okay? So that means your water is not boiling. As soon as you remove that radiator cap, what have you just done?
You jump.
Depressurize the system. Now all of a sudden your liquid, your coolant could have been 218 degrees, right? It was liquid because it was pressurized. You know, it can't boil under that pressure. But now all of a sudden you depressurize it. Now all of a sudden that liquid boils at 212 degrees. It's at 218 degrees. All of a sudden that liquid instantly boils. You have instant gas bubbles that appear inside that liquid. Guess where all those bubbles want to go?
Out.
Out. Where's the highest point in my coolant system?
Your engine bay.
The radiator cap. Guess where your hands are as you just pulled off the radiator cap?
Radiator. Yeah.
Right there. So you're going to get literally scalding hot, boiling coolant spraying out because all the bubbles rushing out of the radiator cap. You're going to get it all over you. You're going to get instant third-degree burns. So, this is a safety thing. We never, ever, ever take a radiator cap off of a hot engine. We always let it cool down to ambient temperature. Then and only then is it safe to actually remove the radiator cap. And we do it slowly so then that way stuff doesn't come out and pressurize, okay? So, how do I know that the coolant is at ambient temperature? Let's pretend I walk up on a vehicle in a parking lot. I don't know when it was last driven. What can I do, a simple test, to know that when I open this radiator cap up, I'm not going to get third-degree burns?
It might be easier, but you can just start the car and look at the engine temperature.
You could. There's an even easier, right? You got the hood open already.
Touch it.
Touch what?
The coolant.
Yeah.
The cap? The cap's metal. It's insulated.
The coolant.
What could I touch?
Coolant tank.
Coolant tank? Maybe.
The engine.
The engine.
Engine? You could. That's metal. Sometimes a little harder to do that. Could maybe touch the radiator. That's kind of hard to get at.
Headers.
Headers? Maybe. You could, right? To see how hot that is.
Just feel it.
Yeah, but feel what?
You'll just feel it.
How about the radiator hose?
The shirt.
The upper radiator hose is right there. You could literally go ahead and grab a hold of that. Is it warm? Is it hot to the touch? If it is, I gotta wait. Right? But if I touch it, it's the same temperature as everything else in the engine. Yeah, I could probably open that safely without flash boiling. Okay? So keep that in mind. Now, this is a cross section of our radiator cap here. So you can see here that this right here is where I would normally, oh, that's not a great color for this, but This is where the cap is at. So what I just highlighted here is like this metal piece right there. There's a spring on the inside of this. All right, and that's basically forcing this gasket right here down, and it seals everything up. Okay. Now, just like our oil filter has a bypass valve, so when the oil filter becomes too clogged, it opens up to allow unfiltered oil through. Yeah, you guys remember that? When I pressurize my coolant system and it starts to get hot, it's going to start to expand. Okay, that's just what happens. Unfortunately, because my system is completely filled up, I need to allow that coolant to escape so I don't over-pressurize the system. So let me go ahead and delete this. I got a little bypass valve right here. You see that? So as this coolant raises its pressure up because it's getting hotter and hotter and hotter, we can regulate how much pressure is in that, because then all of a sudden this raises up our little bypass valve, and then the extra coolant flows out into the reservoir tank, maintaining the coolant level in my coolant system, but saving all that extra coolant so when it cools down, it can then return from the reservoir and fill up my tank back again. That's probably a lot of information. Do I need to explain that again? Yeah? Okay. Yes. Hi. Oh, perfect. Thank you.
Thank you.
Yeah. All right. So when the coolant is full, right, we don't want any air bubbles. It's all liquid. We put the cap on here that seals up the tank. So nothing can get in, nothing can get out. As the engine heats up, it heats up the coolant. As the coolant heats up, the coolant starts to pressurize the system, so it raises the boiling point, but it also expands the coolant. All right? Think of a hot air balloon, right? Hey, I got a hot air balloon. How does it go up? All right? I heat air up, hot air rises, but it also expands. Okay? Same thing with the liquid. As it heats up, it's going to expand. It's got to go somewhere. Okay? And if I don't control it where I want to control it, we're going to get a leak. It's going to burst through something. So this cap is designed to have a little valve right here that the coolant pushes up on, and after it reaches there's a limit on how much pressure it can hold. Okay? This cap is 1.4, this cap is 15 pounds. Once we start to exceed that limit on the cap, this little bypass valve opens up and allows coolant to flow through the cap into a little tank. Okay? We'll just end with that one. We'll talk about it here in a second. Now, again, for every 1 pound of pressure that a radiator cap holds onto a system, the coolant boiling point raises 3.25 degrees Fahrenheit. Now, if I'm looking at a temperature of over 180 degrees Fahrenheit, which is very plausible, because again, coolant temperature is going to be between 180 and 210. How fast does a third-degree burn happen if it gets on your skin? Instantaneous. You open up that cap and there's boiling hot coolant coming out of that. That's you right there. The good news is then at any point in time after that, you can go, look at me. And everyone's all like going over here going, huh? Right? You're freaking out because things are happening. Not great. Okay? So, again, it's a safety thing. Just grab the upper radiator hose, feel it. If it feels like ambient temperature, right, cool to the touch, you're safe to open it up, no problems. But if it's hot or it's warm, right, you can't hold on to that hose for any period of time, wait. Now, again, water boils at 212 degrees Fahrenheit. We have a 50-50 mix of coolant or antifreeze and water. We'll talk about what that does to the boiling point. But when I have 15 psi of pressure in my system, the resulting mix is going to boil at 314 degrees Fahrenheit. Okay? So we're raising that boiling temperature up very high because, again, we don't want it to boil. But again, if you open that up, all of a sudden, let's pretend that liquid's 300 degrees, it's going to instantaneously boil because it's below that. Okay, again, the radiator cap vacuum valve allows coolant return to the system when the engine is cooled off. A malfunctioning vacuum valve could cause radiator hoses and possibly tanks to collapse from the vacuum. So just like how I talked about this previously, okay? The vacuum valve, I call it the bypass valve. Right here, coolant pushes up, it allows that coolant to come here and then dump into a reservoir. You can see that a little bit, right? Here's my radiator cap, okay, in my tank. Pressurizes that coolant, it flows through this little hose, and then gets dumped into this tank. We capture it. Once the engine is shut off, once that coolant starts to cool down, right, it's going to collapse on itself. It's going to shrink back down to its normal size. Well, because everything's sealed up in my coolant system, right, it's not going to be able to collapse because we can't really have anything get in. So this vacuum valve does double duty in that it will then take a hose, basically a straw, and take this extra coolant that we siphoned off, and it will actually bring that back in and dump it back into our coolant system as it cools down to maintain the correct level of coolant. Okay? So basically think of this as like, I don't know, you ever get like those sports drinks, you put a straw in it, you like squeeze a sports bottle and like some liquid comes out, maybe like a juice box, right? Then you let go, and then all of a sudden that box goes back to its normal size and it's like trying to suck things in and sucks in only air. Okay? Same concept here, but instead of sucking air in as it expands or goes back to normal size, it'll suck in the extra coolant. Now, back in the day, this is fun. We didn't actually have reservoir tanks. We just had a kind of a hose that goes down to the ground. And as you're driving, your coolant would expand, the valve would open up, and all that coolant would basically go down that hose and just go on the ground. Right? Oh, because it's going. But then all of a sudden, when you cooled the engine down, right, there was nothing to add back into the system, so your coolant level dropped. So back in the day, before we actually added a tank to this thing, you had to constantly be monitoring and refilling up your coolant because it would constantly be dropping. Nowadays, again, we don't have to do that because we have a reservoir tank. All right, a closed cooling system utilizes the cap and recovery reservoir to maintain proper coolant levels in the engine at all times by burping out hot coolant and then later siphoning back in cooled off coolant. Okay, so again, these are some good terms here that we're going to use. Burping out hot coolant, siphoning in back cooled off coolant. That's a fun thing to say, cooled off coolant. Okay, and that's all because it's a closed system. Okay. So again, you eat a big bowl of chili, right? And all of a sudden you're like, oh, my stomach hurts. And all of a sudden you just burp, right? All that gas and air that was in your stomach needs to leave your system. So you burp it out. Same idea, okay? Maybe you've done this before too, right? You eat something, all of a sudden, like you get like a little throw up in your mouth. You ever do that? He's like,
Sure.
right? And then all of a sudden you're just like, well, you kind of swallow it quick without actually throwing up. That's essentially the process that's happening here. Okay, the coolant kind of comes up, and then once it cools down, the engine just kind of swallows it again. But hopefully not any heartburn. By the way, that's a kind of really gross thing to talk about at 8:34 in the morning. Okay, but the next time that happens to you after you eat some food, you'll be like, oh, that's just like what the coolant system does in the automobile. You're welcome, by the way. You're welcome. It's kind of fun. Okay. So siphoning is a technical term there. And once we go on the shop and I show you guys the lab for that, you're gonna have to identify where the coolant reservoir is at. So then that way you could say, okay, this is where I could potentially add extra coolant, but this is where the coolant goes when the engine's hot, and then this is where it gets taken out of to put it back in once it's done. All right, moving on. Which of the following is not a radiator cap function? I like this. I actually got the correct one up on the screen today. Oh, fingers are in the way. There we go. Gotcha. Got him. Emerson wasn't paying attention, so and he doesn't even have his card. Is he sitting in? No. He can sit in the right spot. One.
Well, there's literally like a couple minutes left. It's like less.
Oh yeah, crazy. It's because you showed up late.
You got mine.
Yeah.
Oh, it's not my fault.
Did I get everyone in the back? I think I got everyone in the back row. Yeah. Okay. Good job.
I win.
87% of you got that one right. My goodness, you must be all really smart. Since so many of you got it right, what's the correct answer?
A.
A. Okay. The radiator cap is not, one of the functions is not to absorb heat. Okay. It's to seal the radiator, right? It's to pressurize the system and to relieve excess pressure by burping out any extra coolant. Okay. So we're not absorbing heat through that. But the radiator cap aids other components in the coolant system to allow it to absorb the heat from the engine and then transfer it out to the ambient air. Okay? All right, to conserve horsepower, radiator fans have either thermostatic clutches or are electrically operated. More often than not, modern day vehicles, they are electrically operated through computer controls. Electric fans have the on time of their motors controlled by sensors, relays, and the PCM. What's the PCM? You had it from yesterday's notes.
Powertrain control module.
Powertrain control module, aka, what's a control module? A computer. Okay. So again, we kind of briefly talked about this. I have my computer, so I'm going to just write PCM. Okay, my computer has a sensor. Think of a sensor as like your eyeball or an ear or your finger, right? The sensor is literally sticking its finger in the coolant and it's monitoring how hot that coolant temperature is. Okay? Then it tells the computer, hey, it's 212 degrees, right? It's pretty hot. The computer then says, okay, I'm going to turn the fan on, or the flower in this case. And as this turns, now that draws air through the radiator, which then drops the temperature of the coolant. The sensor says, oh, temperature's dropping, right? Computer's monitoring that. It says, okay, cool, the temperature's below where it needs to be, turns the fan off. Okay? So this is how this works. It's a big loop. Constantly feeding back in on itself. So it turns it on as it needs, it turns it off as it needs. Pretty cool stuff, how we can use that kind of electronics to run a system to allow the engine to operate within its Goldilocks range of temperature. Thermostatic clutches, I'm not going to get into the technology behind that, but that is also kind of cool. Before we had computers and sensors, you had two different metals, and as metals heat up, they expand and contract at different rates. So what you'd end up doing is actually put two different metals on top of one another, and as they both heat up at the same time, both of them expand at a different rate, which means this one actually pulls this one down, which is basically like turning on and off a switch. Okay? So as the engine heats up, it heats up that metal, flips that switch, turns on the fan with the crankshaft. Okay? Then once things cool down, boom, it popped back into place, shutting off the switch, which then turned the fan off, even though the crankshaft is still spinning. Electrical one's cooler. It's easier to understand and easier to actually troubleshoot. Okay, yesterday we talked about a radiator. A radiator being rectangular shape. We talked about how a fan is circular and how the fan, when it's drawing air through the system, is not pulling air through any place that it's not touching. So we're going to get hot spots on our radiator. How do we fix that? Through something called a shroud. Okay, the radiator shroud acts like a funnel to direct the air through the area where the fan is situated. So all this area here that's not by the fan, we can actually basically put a cover over it and then draw that to the fan. So now all of a sudden air has to go through this area to be pulled through the fan. You can kind of see this here, right? I'll see if I can draw this for you. So even though it's a circular fan, we basically have a box that takes the shape from a circle to a rectangle, which then maximizes the surface area that fan, when it's on, draws the air through. Okay, so again, air is coming in all directions here, but then it's only coming out this section there because of that shroud. Okay, and there are different shapes and stuff for the shrouds. Here I've got a radiator. I got 2 radiator fans, but this shroud again allows the air even up here to be drawn down to where the fan is at. That's the whole purpose behind it. How am I doing on time? Not too bad. All right, the thermostat works with a spring-loaded, wax-filled pellet that senses coolant temperature. Most thermostats are set to open between 180 and 195 degrees Fahrenheit. When the engine is at ambient air temperature, the thermostat is closed. Okay? And the reason why it's closed is so that way, when you do start your engine, the engine can heat up as quickly as possible to 180 degrees. It heats up the coolant to 180 degrees. And then what ends up happening is that 180 degree temperature coolant takes this wax that's in here. Okay, there's literally wax, like a candle. Melts it. As that wax melts, this spring is able to pull down on the thermostat, which then opens up this plunger, which then now allows coolant to flow out of the engine block towards the radiator. It's a very low-tech system that works very effectively. Okay, so you can see here, kind of in this area here, inside is the wax. This is literally sitting inside the coolant as the engine heats up. Right, you can see the spring here. Spring pulls down, which opens up this entire top container, and again allows coolant to flow out of the engine block to the radiator. Okay, we are starting to see a small switch from this type of thermostat to a more computer-controlled thermostat, to where now the computer is sending a signal through an electric solenoid, which opens it up. Now it can actually vary how much it opens and closes, when it opens and closes, based off of the coolant temperature that it's sensing from the engine. Okay, so it actually can do a much more precise control to make sure that that engine temperature is much consistent than something like this. But this works well, and I'm going to guarantee you a lot of modern day automobiles still have this type of thermostat in there. Okay, so you can kind of see here kind of a breakdown, right? So this purple part right here is my engine block. As it heats up, right, the thermostat is closed, so it allows the coolant to kind of circulate in the engine block to heat up. Once this heats 180 degrees, right, this plunger drops down, which now allows that coolant to make its way to the radiator. Now, cool part is hey, how do I know if my thermostat's working or not? You can literally uninstall it from your car. You can literally put it in a pot, boil water, right? And you will see the thermostat actually open up, right? If you're boiling water and it doesn't open up, your thermostat's defective, toss it out, put a new one in. If I had a stove, I have some thermostats upstairs. We could actually do this, but I don't think culinary class would like us coming down there and boiling a bunch of thermostats. That'd be fun.
You should actually ask Debbie, that would be cool.
Yeah, no kidding, right? We got 4 minutes. Okay, this is going to be our last slide for today. Again, just like an oil bypass valve, a thermostat has a bypass valve to maintain circulation of the coolant through the block at the heads and the heater core when the engine is not yet warm. Okay. Again, diagnostic purposes, a stuck open thermostat is going to lower the heater output and overcools the engine, which means it takes longer for that engine to hit its range of temperature to be efficient and meet emissions. Okay, so you can kind of see here. Here I've got a little bypass. Whoops. My bypass valve is right here. So again, it allows that coolant to flow from the engine, bypasses, goes back around. Whoops. But again, once that opens, that bypass valve is kind of blocked and allows it to go there. All right, good stuff. We'll pick up on this again tomorrow. We should be able to get through the rest of that presentation. And we'll be off to the races.